Hello everybody, welcome to another MCAT ACE video for the General Chemistry series, and today we are tackling another stoichiometry part of the series, which is going to be part 2 involving limiting reactants and yields. So this is a very common subject that comes up in the laboratory for most undergraduate students, where you are asked to calculate the theoretical yield. If you have an actual yield, meaning some amount of material you've recovered, you're expected to know how to do percent yields. And in order to find the theoretical yield, you need to know which reactant is going to run out first, and that is known as the limiting reactant or limiting reagent, depending on your terminology. And this is a very important concept to master, especially as you head into MCAT. There can very often be questions in relation to stoichiometry where you are predicting how much potential compound could be produced or which compound would run out first. And so that's what we really want to focus on in this lecture series. So just as a little bit of background, when you get to this point in the stoichiometry lectures, we are assuming that you know how to balance equations successfully and that you know how to go between grams and moles to grams successfully. So that is all background material at this point. And if you're not comfortable with that, that's fine. Just go back to the other stoichiometry lectures and you should be covered on that. And you can come up to this point and then start continuing from there. So what are we going to take a look at in this lecture? Well, number one, we're going to just give you a reminder of the importance of balanced equations. So this was in a previous lecture, but we just want to talk about it and remind you. So that's going to be one of the first things. Then we'll look at how to determine a limiting reactant, how to determine theoretical yields, and then actual yields and percent yields. And then finally, I do say practice at the end, like the practice problems we have. This is going to be a very math-heavy and practice-heavy session. So I would suggest two things. Number one, you should definitely have a calculator as you're working through this. And number two, it would be beneficial for you to have a periodic table. So keep in mind, for the sake of screen space, I'm not going to put a periodic table up and then keep deleting it and putting it up. So I have one next to me here. I have my problems worked out. But as you go through this video, I suggest that you pause it, work on this yourself. You're going to want a periodic table handy because we're going to be doing a lot with molar mass during this entire series. So if you have those two things ready, let's go ahead and take a look at some of the limiting reactants and theoretical yield questions. So here we go. All right. So this is an example question, and the way I'm going to run this lecture, I'm going to do this one, we'll run through it, sort of give details, then we'll do a second one together, and then the practice, the questions, which I'll try to frame as multiple choice, are going to be your third practice set. So by the time you finish this video, you should have 3 practice problems that you have been able to do hands-on experience with. All right? So let's take a look at this problem here. We've got an example where lithium metal is reacting with water in order to give lithium hydroxide and H2 gas. All right, so that's the equation up there. And let's take a look at the actual question that's being posed here. A 23-gram sample of lithium metal is reacted with 27.5 grams of water. So note that they are telling you here both the amounts of compound, how much lithium, how much water, on a gram basis. All right. Now, given this reaction, determine, and you can see A, B, and C, the limiting reactant when producing hydrogen gas. So we're framing this question by saying, I'd like to produce hydrogen gas. So which of these two reagents is going to be depleted or run out first when attempting to make hydrogen gas? And we'll show you how to do that. That's, determining a limiting reactant. So then in B, what is the theoretical yield of hydrogen gas? So based on the amounts given in this problem, how much hydrogen gas could I theoretically produce? That's my theoretical yield. And then C, once I've obtained the theoretical yield, the percent yield of hydrogen gas if 1.25 grams of hydrogen gas was made. So what is this saying? This is saying if I ran this reaction in a lab and I successfully obtained 1.25 grams of hydrogen gas, I would like to know how successful is that in comparison to my theoretical yield. This is called percent yield. And percent yield out of all the math is really the easiest to perform because you're just taking actual yield, dividing it into theoretical yield, and then you're doing a multiplier times 100. So just think about like when you have exams, your theoretical yield, so to speak, would be 100 points on most exams. You could get 100 points possible. Your actual yield of points would be whatever you get. So let's say that you get an 85 out of 100. We all know as people who are pre-med that would be awful, right? But let's say that you got an 85 out of 100. And if you have an 85 out of 100, you take that, you get 0.85, you multiply it by 100, that's 85%, right? And most students, they don't even go through all that logic in their head. They just know, they see the number, it's out of 100, and they know what their percentage is, right? But if you take 85 divided by 100, it's not 85, it's 0.85. And then you need the multiplier in order to do that. So that's what we're talking about here, all right? This would be your theoretical yield. How much could I obtain out of this reaction versus how much did I obtain, and then multiply that by 100, you get your theoretical yield. I'm sorry, you get your percent yield, but the theoretical yield is in that. All right, so the first thing, and I mentioned it in the brief overview here, before you ever start a limiting reactant problem, and I would state in general a good rule, before you start any chemical problem, because we're going to see titrations later on and redox reactions and all these types of things, balance your equation. The importance of a balanced equation cannot be overstated here. You need to have a balanced equation. The balanced equation, as we talked about in the balancing equation lecture, Stoichiometry Part 1, is your recipe card. It tells you exactly how many chemical reagents you need on a mole to mole ratio. All right. And so if I don't have a balanced equation, I'm not going to be able to complete the rest of these questions. So we need to balance the equation. Now, let's take a look at what we have here. If I were to balance this equation up here, I would suggest you attempt to do it. So pause the video and then you can walk through. This one shouldn't be too hard. All right. So if you take a look at this, you would say, all right, I've got 2 for the lithium over here, right? I'm sorry, I have 1 lithium and I have 1 lithium. I'm jumping ahead here, okay? So that's fine right now. The lithiums are fine. Now, I go to the hydrogens. I have 2 hydrogens due to the water on the reactant side. I have 2 hydrogens due to the hydrogen gas, but I have another one due to the hydroxide here, right? So you have to keep in mind, if I don't balance out this hydroxide, the H2 and the H2O, they come as sets of 2, right? Because of the subscript. So this hydroxide will always throw this off balance. What I mean is if I ever attempt to just balance using this and this, they're both an even multiple. And so I will always add 1 additional hydrogen here, which will throw it off, all right? So when balancing this, I would say, all right, so what I need to do then is I'm going to need to put a 2 in front of here. That will give me 4 over here now. And at that point, this makes sense because then I can put a 2 in front of here, and this would now be 4 for the hydrogens. So the hydrogens are balanced at this point. What I need to then check on is my oxygen. So I have 2 oxygens here. I have 2 oxygens over here, so that looks fine. And then if you go back, you do your final check, you'll see the lithiums are no longer balanced, so I just need a 2 in front of this lithium metal here, all right? And then once I have that, this is now a balanced equation. So that shouldn't have been overly complicated for you compared to some of the other examples that we've seen in the previous courses. So a 23-gram sample of lithium metal is reacted with 27.5 grams of water. Given this reaction, determine. All right, so the first thing we need to determine here is the limiting reactant, all right? And it's based on hydrogen gas. So what I want here are the molar ratios of each reactant to hydrogen gas. So I'm going to mark this down here because we're going to have to scroll down as we do the math. There are 2 lithiums, all right, for every 1 hydrogen gas. And there are 2 waters for every 1 hydrogen gas produced. So we want to keep these ratios in mind as we're working through the limiting reactant. So I've got that note there for myself. All right, now what I want to do is I'm going to come and I'm going to say, all right, the 23 grams of lithium, this is the first one that I'm going to solve. I have 23 grams of lithium. You need to convert into moles. You cannot directly take grams of one compound and convert it into some other type of compound without moles. So I need the molar mass of lithium. That would be 6.94. Remember, I, in these lectures, will take these out to 2 decimal points, and that's in every 1 mole of lithium. Now, this would give me moles of lithium, and a lot of students, you need to be careful of a pitfall here. A lot of students will turn around and say, I have moles of lithium, I have moles of water. They'll do the same thing for water, and then they stop and compare that. That, to use the analogy, is comparing apples to oranges, okay? Because a mole of lithium is not the same thing as a mole of water as far as the molar mass and the number of lithium atoms versus water molecules, etc., when you are dealing with these on a molar mass basis, okay? Now, 1 mole of water molecules and 1 mole of lithium would be 6.022 times 10 to the 23rd of those molecules, but again, we have varying grams amounts here. So on a molar mass basis, on a per gram to mole basis, that is not a good comparison. So what we do to find limiting reactants is we then turn around and we move this over so that we have the hydrogen to hydrogen comparison. So remember, we said that there were 2 moles, and this is coming from the balanced equation right here. There's 2 moles of lithium to every 1 mole of H2, right? The H2 gas. So now, if I solve that, that is an equal comparison. All right. Now I'll give you a minute if you're working with your calculator. I'll set the other one up here. All right. So the other one said that we had 27.5 grams of water. Now, with the 27.5 grams of water, the molar mass of water, pulled from the periodic table I'm working with, is 18.02 grams of water for every 1 mole of water. Okay. Now, again, I want to convert the water here. So, wait a minute. I got 2 here. Okay, 2 moles of water for every 1 mole of hydrogen gas. Right? So, we turn around and we solve for both of these. You should, at this point, see that the lithium is 1.66 moles. And this is moles of H2 gas that could be produced. Okay, the little subscript G, these are states here. When we have S is solid, L is liquid, G is gas, and AQ would be aqueous. And then I turn around and I have the water, and that's 0.763. So what this is saying is, based on the amounts of lithium metal and water that I have present, the lithium has the potential to produce 1.66 moles of hydrogen gas, while the water has the ability to produce 0.763 moles of hydrogen gas. The lesser of the two is the limiting reactant. So this one right here, I can produce a lesser amount of H2 gas here, and therefore the water is considered the limiting reactant. So we have now answered part A. This is water. That's the limiting reactant. All right. So remember, we need to compare an apples to apples type of situation. Moles of H2 gas produced in each case is going to represent a proper comparison, not moles of lithium and moles of water. You need to convert those into potential moles of H2 gas, or in some other equation, whatever your product of interest is. Now, we're actually very close to the theoretical yield. This actually is a theoretical yield right here, okay? But it's in moles. So most of the time, theoretical yield, not always, but most of the time it's stated in grams. And so what we're going to do is we're going to take this one step further in part B here. All right, so this was part A. In part B, we're going to determine the theoretical yield in grams. So what I would need to do is take that lesser amount, right? So this is moles of H2 gas. And then all I need to do is run this through with the molar mass. So I want moles to cancel out. So when I use molar mass, it's 1 mole of H2 gas. And then what is the molar mass of H2 gas? It is 2.02. Because you have 1.01 for every hydrogen. And there's 2 of them because it's a bimolecular compound. So I have grams of H2 gas. Simple multiplication here will tell me that the potential theoretical yield would be 1.54 grams of H2 gas. So now this is the theoretical yield. This is how much, based on the amounts given in the problem, this is how much hydrogen gas I could theoretically produce based on this problem. All right. So now the next thing that I want to do is I want to finally find out what is the percent yield of hydrogen gas if 1.25 grams of hydrogen gas was made in the laboratory. All right. So just fair warning, I'm going to clear the board here for this last part. Okay, so copy this down, pause it if you need to. So let's clear this off. Keep in mind the 1.54 grams. That's our theoretical yield. We're going to need that in a second here. So I calculate the percent yield by doing the following. I'm going to say my percent yield is, well, my actual yield, which is 1.25 grams, over my theoretical yield, and that's the number I told you to just remember there. It was 1.54 grams. So if I take this times 100 for the percentage multiplier, that will be the percent yield. So if you run that through your calculator, it should only take you a second. 81.2% is the percent yield that I have obtained here. So if you think about that, what I'm saying is if I got 1.25 grams of hydrogen gas from my reaction, the potential was 1.54, then my success rate was about an 81.2% recovery out of what I could have theoretically made. Now I want to stop off here just for a second to talk about this sort of theoretically. Many reactions, not all, but many reactions fall short of 100% yield, and it's just impossible to get the 100% yield. And many students will come up to me when they're working in the lab or something like that, and they say, oh, I got it, an 85% yield, or some will say I get a 50% yield, and they'll say, is that acceptable? It depends on the reaction, all right? So certain reactions, for instance, organic chemistry reactions, have notoriously low yields because they have lots of side reactions, the conditions are very fragile, or something like that. So there are some reactions, okay, where a 50% yield may be considered the gold standard. That means you had an excellent recovery in that particular reaction. So all this is stating is how much we actually recovered. It may be in certain reactions, you have side reactions, and it's very difficult, if not impossible, to recover 100%. So I just wanted to sort of put that note out there because that many students will come up with that often. You probably won't run into that theoretically on the MCAT because you're not actually in a lab doing the lab work when you're taking the MCAT. But I just wanted that as an aside because it often comes up as a question theoretically. All right, so what I'm going to do here, I'm going to clear the board. I'm going to put up a new problem. And what I really am going to encourage you to do is to take the new problem, work through it, and then you can unpause it and I will go through it. And then again, I have a third one that I'll put up there, and for that one, you will be able to continue and get more practice. That one will be framed slightly differently because I'm going to leave some multiple choice questions in the spirit of an MCAT type of situation. So let me clear the board here and I'll bring up the new question. Okay, everybody, so hopefully you can see the new problem here, which states if 15.5 grams of ammonia gas reacts with 17.3 grams of oxygen gas, how much water could be produced? Assuming 11 grams of water was recovered, what is the percent yield? So what this is really asking you here is determine the theoretical yield of water and then determine the percent yield of water. Now, keep in mind, in order to determine the theoretical yield of water, you will need to determine which reactant is the limiting reactant. So in the first question, I sort of broke it down into micro steps so that you understood what you were doing. This is more how a question might be presented on an exam or even on the MCAT in some cases, although you'd have your multiple choice answers, right? This is 2 questions in one here. But you are being asked to determine the limiting reagent here first, because after that, that's the only way that you could get the theoretical yield. So I would suggest that you go through this problem, you attempt it, so pause the video here, see if you can get all the answers, and then unpause it and walk through it with me. All right, so I'm going to get ready to start walking through this. Hopefully everybody had a chance to work on it. And again, if not, I strongly encourage you to at least get as far as you can before unpausing the video here. All right, so as far as balancing, for the sake of time in this video, because we've already done a balancing video, I'm going to give you the final numbers here. All right, but it would be 4, it would be 5, it would be 4, and it would be 6. All right. Now, I will just let you know as a brief side note, you did have to use a fraction in this one in order to make the balancing work out. If you did it through an easy method, you did need a 5/2 over the O2 here in order to get it to work out, and then multiply through by 2. So just a side note there in case anybody was sort of stuck on the balancing. All right. So now, if I have 15.5 grams of the ammonia and 17.3 grams of the O2, let's just start right off by finding the limiting reactant here, okay? So what I'm going to do, again, because I scroll down here as I work on this, I'm just going to note my ratios. So I have 4 ammonia to every, and we're interested in water here, to every 6 water, okay? And then I take a look at the other one. I've got 5 moles of O2 to every 6 moles of water. Perfect. So again, these values come from the balanced equation, right, when I'm working on my limiting reactant. So let's go ahead and set up the math here. Hopefully you were able to get started on this and get this far. So 15.5 grams of the ammonia. We'll start with the ammonia gas here. Okay. So if you go to the periodic table, again, out to 2 decimal points, grams of ammonia, I got 17.04 for every 1 mole of ammonia. And then I need my molar multipliers here, the ratios from the equation. So I keep in mind that I want to get rid of the moles of ammonia, and that was 4 based on the equation, moles of ammonia. And then the water was 6. So I had 6 moles of H2O. And I run through that, okay? If I solve the entire set, it should be 1.36 moles of water. And that would be what I would expect for the ammonia gas. All right. Now, I also need to compare the O2. So for the O2, I had 17.3 grams of O2 gas. And in this case here, 1 mole of O2 gas is going to be, now keep in mind it's O2, so you shouldn't have 16 down here. You want 32 because you need to double it up, just like the hydrogen, which was another one of the diatomics. Okay, grams of O2. And now my ratio of O2, as I'm going through, I would expect 5 moles of O2 for every 6 moles of water. Okay. Now if I solve this one and I plug this one into the calculator, I get 0.649 moles of water. So it should be obvious at this point that the O2 gas is going to be the limiting reactant. So let's move this over and take this to theoretical yield, right? That's my next step. So if I know that my maximum potential output is 0.649 moles of water vapor, then I can expect that for every 1 mole of water, the molar mass, which you should have handy, we used it in the last problem, is 18.02 grams of water. And so what would the theoretical yield of water be? Turns out to be 11.7 grams of H2O. This right here is our theoretical yield. So we've determined the limiting reactant was oxygen. The theoretical yield is 11.7 grams of water. And now to finish this off, the only thing that's left is to find the percent yield. Now the problem told us, let's see what it said, 11 grams of water was recovered, right? So what I can do here is I can say I've got 11 grams of water, and this is going to be in comparison to 11.7 grams of water, because that's the maximum potential, that's the theoretical yield, and I would do a multiplier times 100, and you should have come out with 94%, and that would be the percent yield for this problem. All right, so hopefully everybody understands the general process here, but let's just state it one more time. And of course, we're going to talk about this when we do our recap or our review. You want to balance your equation properly. You have to get the molar ratios set in order to do this. Once you have the molar ratios in place, you can then turn around and you can start figuring out the gram to mole breakdowns for the product of interest. So the next step is find the limiting reactant. We find the limiting reactant by taking the grams of each reactant present, converting it to moles, and then using a mole-to-mole ratio found in the balanced equation in order to find moles of product to moles of product. And that's where we make the comparison and the official call on the limiting reactant. Now, once we have the limiting reactant, we know how much of that given product we want can be produced on a mole basis, so we can convert that into grams using molar mass. And then finally, once we have that theoretical yield, we can compare it if we have an actual yield in order to determine the percent yield or the success of the reaction overall. All right, so that's the general outline. That's the process that we're following here. So I'm going to clear off the board here one more time, and I'm going to bring up the questions. These will be formatted in more of a multiple choice type of situation to try to bring some relevance to the MCAT. However, keep it in the mindset of what we just did here. You're going to be executing your math in order to find these proper numbers. Okay, so let me clear the board. We will do that, and then we'll do our recap, and we will be set for this lesson. So I will see you guys in a second after I wipe the board. All right, everyone, so here we go. For the question, use the following material to answer questions 1 through 3. So similar to an MCAT, this is a passage type of question where you're going to be given some material and then you have to answer multiple questions based on that material. So you see a reaction up here, all right, and it says a chemist reacts 10 grams of titanium chloride with 19.7 grams of magnesium metal. So here are the questions based on that. Number 1, what is the expected molar ratio of titanium chloride to magnesium metal? You have a couple options there. Number 2, how much magnesium chloride could be produced? You have several options there. And then, number 3, how many recovered grams would lead to a 50% yield? And you see the numbers there again. So this is a good representation of theoretical yields, limiting reactants, and percent yields. So pause the video if you need to go through these. I'll scroll through them here once again. And you should attempt to try these, and then we'll walk through them together before doing our review. All right, so let's take a look here. Okay. Now, hopefully everybody had a chance to practice this and pause the video. So I'm going to be going through this here. If I balance this equation, which is the first thing we should do, we should always balance the equation. All right, it ends up that I need a 2 in front of the magnesium, and I need a 2 in front of the magnesium chloride, and that will balance this equation here. So a chemist reacts 10 grams of titanium chloride and 19.7 grams of magnesium metal. So it's telling us of the 2 reactants how much of each we are utilizing. All right, what is the expected molar ratio of titanium chloride to magnesium metal? So this should have been the easiest of the bunch probably. Hopefully you eliminated B. 10 and 19 are simply sort of a response to draw you in based on the gram numbers that you see here. That has nothing to do with the molar ratios. Now the molar ratios, okay, come from the balanced equation. So all you needed to do here was look at titanium chloride to magnesium, and you see that the ratio here is 1 to 2. So the answer would be A, 1 to 2. The rest of these would not be correct based on the balanced equation. So the key to answering this question right here is that you needed to balance the equation above. That's where you're going to get that material from. And I kind of set this up as a block or a road check to make sure that you balance the equation before you just jumped in head first to the other material. All right, now how much magnesium chloride could be produced in this case? So now we need to determine limiting reactant and theoretical yield. That's what this question is asking us here. So let's get started on this. I know that I have 10 grams of the titanium chloride. Now, this one would be the most time-consuming problem because I would need the molar masses, and there's going to be quite a number of calculations involved. So titanium chloride, if you pull it off of the periodic table, would be 189.68, and that is grams of TiCl4 for every 1 mole of titanium chloride. Now, the next thing that I need to do, because I'm interested in magnesium chloride, is use the molar ratio here. So if we look, magnesium chloride had a 2, titanium chloride had a 1. And so I would say that for every 1 mole of titanium chloride, I'm going to have 2 moles of the magnesium chloride, right? So that's one step. That will find me, for the titanium chloride, the potential amount of magnesium chloride that could be produced. You run that through the calculator, and you find 0.105 moles of the titanium chloride that could be produced. So now I need to do the same thing with my other reactant, the magnesium metal. So I was told that I have 19.7 grams of the magnesium metal. Okay. And then once I have this, I can simply pull the value off the periodic table for the molar mass of magnesium metal, which is 24.31 on the table I used. That's for 1 mole of the magnesium metal. And then the next thing would be to do, again, the molar ratio. So I scroll back up here, and I have a 2 to 2, so that's a 1 to 1. Now I'm going to put it here as 2 to 2, just to keep it. But keep in mind that these would cancel, so there is nothing wrong in this case if you decided to put 1 to 1, because that would also be proper here. So this is 2 mole, forgot the mole up here, the unit. It's 2 moles of magnesium chloride to 2 moles of the magnesium metal. Again, 1 to 1 would also be acceptable here. I just don't want to confuse students that might have trouble following where this is coming from in the balanced equation. So you run all of that through, and you find 0.810 moles of magnesium chloride. So right here, the lesser amount is the limiting reactant. So we now know that the titanium chloride is the limiting reactant here. So what I'm going to do is I'm then going to take the moles, the theoretical number of moles of the magnesium chloride, and I'm going to multiply that by the molar mass here, right? So I can do this as drew a multiplication there. I can do that as my table here, because I usually set them up as tables. And what I find is that for every 1 mole of magnesium chloride, the molar mass is 95.21 grams of magnesium chloride. So if I solve for that, that would be my theoretical yield, and it comes out as 9.997. So when I round this up because of significant figures, because I only have 3 significant figures in this answer, I'm going to end up with 10.0 grams of magnesium chloride. So there's the answer. This one was best just directly solved and not attempting to take a bunch of guesswork. Right? Now, there's really almost no math in the third one. You could technically do math because we know now that the theoretical yield is 10 grams, but how many recovered grams would lead to a 50% yield? And the answer here would be 5, because 5 out of 10 is going to lead to the 50% yield, right? If I were to actually draw this out, I say I get 5 grams of the magnesium chloride. There's a total of 10 grams that could have been produced times 100. This should have been an obvious 50% yield right here. All right, so that was the set of questions for limiting reactants. Hopefully at this point you have enough practice with this that you're starting to feel comfortable with these types of questions, both the balancing equations and determining multiple ratios and limiting reactants / theoretical yields. So let me clear the problems off of the board here, and then we will do a recap of the material that we've just discussed. So give me a second to do that, and we'll go over the brief recap. Okay, everybody, so here I have put up the summary of what we've discussed during this lecture. So number one, the most important thing that you want to do is to balance the chemical equation first. You've heard me say this before, you're going to hear me say it again. You need to balance chemical equations. That is where the starting point is going to be in terms of each of these types of reactions that we're discussing here, right? Now, this is where the molar ratios are going to be found. So when we discuss molar ratios are not grams converted to moles and then comparing them to something else. Molar ratios are the coefficients, the large numbers, used in balancing the equation. That tells me how many moles of one compound can lead to or be used with how many moles of another compound. All right? Now, these numbers, these molar ratios, can convert reactant values over to product values. So that's how I can determine how much, hydrogen gas I could get from lithium metal or something like that, one of those examples we used. So how much of a given product can I produce with how much of a certain reactant? And that is used only through the molar ratios. That's how you obtain that. All right. Now, most of these questions, the limiting reactant questions, are going to give you an amount. Usually it's in grams. Sometimes it might be in moles, but usually it's in grams. So you want to use that amount that's provided. All right. So if they say you have X number of grams for compound 1, you have Y number of grams for compound 2, you're going to use those values. That's your starting point. Always start with what you're given. Take those gram values and convert them into moles of reactants, right? So if I have two reactants like ammonia and water, convert the grams of ammonia to moles of ammonia, convert the grams of water to moles of water, just using the molar mass. But don't stop there. That's key. You need to convert the moles of reactants into moles of products. So this is when we were talking about apples to oranges versus apples to apples type of comparison. When we get started with this, we need to take these equations through to moles of a similar product so that we can compare how much could reactant 1 produce on a molar basis, how much could reactant 2 produce on a molar basis, right? And once we have those values, then I'm comparing the apples to apples, then I can turn around and state which one is going to be the limiting reactant, because the lesser of the two, the one that would run out first, will be the limiting reactant, and that's what I'm going to go for there, right? So once I've determined the limiting reactant, I really have my theoretical yield, but I have it on a molar basis. I want to convert it to grams. So you're going to take that lesser molar value that the limiting reactant provided and then multiply the moles of that potential product by the molar mass of that product. And the grams that come out of that, that will be the theoretical yield in grams for that reaction. Now, if the question was asking you for it in moles, then you would already be set at that point, all right? So if an actual yield is provided, not all questions will give you one, but we checked it out in multiple situations here. If you are given an actual yield or a certain amount that was recovered in a scenario, then you can divide the actual yield into the theoretical yield. You use your times 100 multiplier, and that'll give you the percent yield, or in other words, the success. How successful was the reaction, and that's percent yield. All right? So I think this covers everything that we wanted to go over. We talked about how important the balancing of equations was, and we did that multiple times. We were able to successfully identify limiting reactants by taking the given amounts of those reactants and converting them into moles of potential product and comparing those values. And the lesser of the two values was the one that we said would be the limiting reactant. We then were able to determine theoretical yield by converting that into grams using molar mass of the product that was of interest. And then finally, we could, if we were given an actual yield, determine percent yield. So that covers what we set out to do. So thank you very much for taking the time to learn with us on MCAT ACE. And again, this is the second part of the stoichiometry lecture. There will be continued parts. We have to do titrations and other things. But we will see you guys for future lectures, and thank you so much.